So welcome everyone to week 16 of our series Get Started in OpenSees with STKO. Hi Hernan, welcome. Please do turn off your mic just for the beginning. So we're gonna have another 30 minutes discussion about nonlinear time history analysis today. So we're almost at the end of our course series. We will tackle the topics of model and response spectrum analysis, and then we're going to just discuss specific topics related to modeling frame structure in RC, steel, and masonry. So let's say next week is our last theory theory class about model and response spectrum analysis, and further on we're just going to discuss about some specific topics related to specific material of frame structures. So, about nonlinear time history analysis. I'm sure you guys know that there's been a big webinar that Dr. Petraka did on nonlinear time history analysis. So I'm not going to go into like very high complex topic or specific theory aspects of nonlinear time history analysis. I'm just going to go through the basics of performing this kind of analysis in OpenSees and STKO. So hello everyone, hello Hernan. So just to tell you what you need to perform nonlinear time history analysis in STKO, you will need to define time series with the accelerations that you want to apply to your structure, or if you want in terms of velocity or displacement, depends on what you want to apply to your structure in terms of dynamic input. Then we will need to define mass and damping, damping properties that the structure needs to have, and then define how the excitation is going to be inputted in the analysis. There are two ways that we can do that through OpenSees. One is the uniform excitation and one the multi-support excitation. 3D frame structure with rigid diaphragm, and we have 24 base nodes. So these are the nodes at which normally in any nonlinear time dynamic analysis of a civil building, we want to apply our uniform excitation or multi-support excitation. Sorry, there's a typo here. We talk about Guzman, could you please mute your mic? Thank you. Today is a bit of a challenge. Okay, so this is our structure. What we're gonna do with it? We need first to define a time series. The time series that is used to do nonlinear time history analysis is the time series path that you can find in our definition editor. Of course, if you're just using OpenSees right away, you will have to source this information through like an external text file that needs to be formatted in a certain way so that you can parse it in your OpenSees. But in this case, it's really easy. With STKO, you just load a vector of the value of the acceleration that you want to input in your model, and then you can choose if you want the application to be constant, or just let me show you in STKO itself. So then you can choose if you want your application to be constant or non-constant, so following a specific function. Then after that, you can set two different things. The factor by which you want your accelerogram, for example, to be multiplied for. And just remember that you have to be consistent with your units, as always in OpenSees and STKO. So if your model is in Euro-millimeter square, your acceleration needs to be in millimeter seconds cube. So it doesn't have, you cannot use the meter unit, and just be careful if you're using something that is in G and transform it back to millimeter per second square, second cube. Why do I say cube? Second square, yes. Then you have to input what's the DT of your analysis, and this will define the length of your analysis overall. And this value here, if I go back to the presentation, is actually the value that will define the duration of overall your transient analysis. This is because when you define in the analysis step the duration of the analysis, you have to refer to the time series that you're applying. Because if you want to capture the behavior of the building subject to the input of this whole accelerogram, then you need to reference the whole duration of it, not to lose parts of your response if you cut your analysis too short, or if you make it too long, you will not be able to match the response with the accelerogram itself. So in fact, as a let's say a beginning data that you input in your analysis steps, you set the number of increments equal to the number of values that you have in your accelerogram. Or anyway, referencing the dead t, you can divide the duration by the interval at which each value is been recorded. This is because, I mean, this is just a general rule that you can start with, and then you can go lower. So trying to have a higher number of increments and a lower dead t, so that you can capture an even better response. So this is just as a base for you not to miss the response of any of these points. Further on, you need to define the mass. So the dynamic analysis of any kind requires the presence of mass in your model to account for the inertial forces. This is because mass and weight are separate concepts in OpenSees. This is not something that gets automatically transform one into the other. There is the possibility to apply mass inside of some elements, but I always suggest people or anybody to apply mass as a nodal mass. Of course, there are tools in STKO that you can use to apply your mass as a face or on an edge or on a volume, but all of these masses are just going to be applied on nodes via some of our internal calculations that we do. This is just for you to, let's say, ease up your operations of load assessment, so and load and mass assessment in this case. So if you just know what's the density of a concrete slab or the density of steel of a column, you can just apply that value to an edge or to a face, so that you will not have to do the calculation yourself. STKO will do them for you, and we distribute that mass equally on the nodes of the elements corresponding to that face or that edge. Masses don't need to be referenced in the analysis step. So if you go and see in the model, you will see that masses are not changing colors. So masses will always be black in the conditions in the work tree. And of course, if you don't have mass, you will not have any results, either in eigenvalue analysis, of course, or in dynamic analysis or nonlinear time history analysis. Then we can add something else. So our system can be undamped, or we can add possibility of the presence of damping. So in OpenSees, damping is not defined as a percentage, but it's defined by a specific set of parameters. We have a tool inside inside STKO that kind of computes Rayleigh dampings by itself. You just have to define. Let me show you directly inside. Wait, sorry. So the calculation is automatic, but you can also do it manually by defining alpha and beta. But in the automatic calculation, you will see that Rayleigh damping parameters are calculated automatically based on your structure, and you can just define if you want to be used the current shifted initial system or the committed stiffness. Assign inserting this inside of the analysis steps assigns damping to all the elements that have been previously defined in your model. So let's say that you're using the region command. I don't know if anybody of you has ever used this command. So you define a region of your structure, let's say maybe using a specific selection set that you have defined before, like for example, all the faces of your structure. And then you save it. And for some reason, you want to remove these elements from your structure, like using a model subset, or using a model subset, or in some way removing that element from your structure, then the damping will not be applied to that element. Or for example, if you're using constraints that are being added afterwards, after that the damping parameter is there, the damping will not be applied to that newly constrained structure. So as we define the time series, mass, and then we define damping, what we need left is just an excitation. So the most common command that is used in OpenSees and STKO is the uniform excitation. This command applies the uniform excitation to all the fixed nodes in a model. This is not a condition, it's just an analysis steps. So you don't need to create a load in the condition like any load pattern, even if this is an input that you're giving to your analysis. In this case, you have to just define the direction in which you want the excitation to be acting, and the time series reference in that direction. So if, for example, you have an accelerogram that goes in 2 directions, and you have also vertical seismic input, and you want to input it there, you can just create as many uniform excitation as you need. Just define the direction that you need to define, and reference the appropriate time series previously created. You have to keep in mind that in this case, using a uniform excitation, the results will be relative in respect to the result at the fixed node in the model. This is because let's say this kind of analysis considers the base, so the fixed of the model, to be not moving. So it's just we are watching the results and seeing the results in reference to the movement of the base. Of course, we know that dynamic analysis, the base is moving as the ground is moving if you're doing a seismic input, but the results are going to be relative in that respect in this case. Instead, there's another instance in which they're not. I'm going to just show you right after. So once you've done that, you can define your transient analysis setup. It's not much different than setting up a static analysis setup. Most of the things are the same. So let's say in this case, we kept all our constraint handler because the constraints of our structure did not change. We kept the number, we kept the system, we kept the algorithm to find convergence, and we kept also our convergence test. In terms of displacement increment, what we need to change is the integrator. We need a transient integrator now, not a static anymore. And of course, the type of analysis that will enable the possibility to select one of the transient integrator transient integrator available in STKO and OpenSees. Define which are the parameters relevant to this. We discussed this in, I think, week 10, how to define the integrator parameters. And anyway, these are the most common parameters that are used in nonlinear time history analysis. So if you do in dynamic analysis in general, numeric method with these parameters is unconditionally stable. So I would suggest you start with this. And then we have to set up the analysis duration and increment. As I said before, we reference our the duration of our analysis has the duration of our accelerogram, and then we set the number of increments based on the number of data that we have, or let's say the duration divided by the time interval. That's it. It's not very complicated. There's very few things to adjust if you want to pass from a nonlinear static analysis to a nonlinear dynamic analysis. But it's just very important that if you want to consider damping, you need to input it. And if you want to consider, and if you want to do any dynamic analysis of whatsoever, you need to input mass too. There's another way that this can be done, which is, okay, I just wanted to show you how this can move forward. So as you see here in the analysis steps, I set up the uniform excitation, the damping, and the transient analysis right after my static and eigenvalue analysis. I don't have any more the horizontal load from the pushover, and I have mass defined at each node of the structure. So what you can do, you can monitor, for example, the acceleration at the top level in reference to the time of the analysis, and see how can this follow the accelerogram that you have, and how the stiffness and rigidity of the structure can impact the response in terms of acceleration. Another way in which this can be done is the use of the ground motion and the multi-support excitation. So if you want to capture let's just go big forward. If you want to capture the ground motion, the motion of the fixed base of your structure, you need to use a different way, not the uniform excitation, but the multi-support excitation. Multi-support excitation is actually defined through first a condition, which is the ground motion. You can define as many ground motion as you want. And this is probably very useful if you have a very large structure and you want to, or a very large portion of soil that you're modeling, and you want to capture the impact and the response due to different ground motions in different positions of your structure. For example, if for a very long infrastructure, there could be different values of accelerogram or anyway seismic input at one end referred to the other end. So to do this, you need to define as many ground motions as you need, and then compile them into multi-support excitation. So the ground motion has to be applied to the nodes that you want to excite. It's not the same as the uniform excitation before, that was not a condition. This is actually a condition. And then after being applied, of course, you have to define if it's an acceleration or if it's a velocity input or a displacement input, and by which factor you want it to be incremented or decremented. And just a note on this, as you saw before, there's a factor in the time series too. So for example, in this case, just be careful not to factorize or anyway, apply a factor to your accelerogram twice, because it can be an error that's done very commonly. And then this ground motion has to be, let's say, listed in a multi-support excitation that allows the possibility to create a vector of ground motion that we want to input inside of our dynamic analysis. In this case, the result will be absolute in respect to the movement of the base structure. So just a little simplification. On here on the left, you see for a uniform excitation, the base of our structure is not moving at all. Instead, for a multi-support excitation, the base of our structure is moving together with it. So we will be able to see an absolute value in terms of acceleration, displacement, etc. Normally, what people want to see is like relative displacement and absolute acceleration. But in the end, even the use of uniform excitation can be, let's say, you can have the same result as for the multi-support excitation if you're using one single ground motion with the uniform excitation, just by adding, let's say, the accelerogram input to the value of acceleration response of your structure. And this can be done easily through the Python API, for example. So just to show you very quickly in the model how this is done, we have our additional definition. Then we have our mass defined here. Then after any analysis that we want to perform before, we add the uniform excitation, we add the Rayleigh damping, and we create our transient analysis with our different integrator and different analyze command here. What we can do is also the other type. I prepared another example with the other type of analysis. There you go. So we have, instead of just having the mass, here we have our ground motion applied to the base nodes with the referencing the time series that we want to use in terms of acceleration and in the direction that we desire. Then we can apply damping in the same exact way that we did before, just with the automatic tool. And then we're going to do transient analysis in the same exact way. So this is not, it doesn't really change so much. What I just wanted to show you is a way to extract your results. So if you create a surface plot, these are the results for the uniform excitation. Okay. A very easy way to do is just show your nodes, put yourself in a frontal view, extract data on the nodes, for example, in terms of acceleration, the x direction at the base. And I don't know if you guys know what to expect in this case. We'll have 0 because we're at the base, so we don't expect our building to move at the base. Then if we want to see instead the development of acceleration at the top of our structure, subject to this nonlinear time history dynamic analysis, acceleration top, we can say I want to see the maximum and create a chart in reference to it. So Then if we want, for example, to see results in terms of, let's just deselect and select only the nodes. I want to see, oh, this is why the graph was a bit weird. I had selected too many things. So let's do first the acceleration again at the top without the combination of 0. Exactly. So this is what I'm expecting my structure to behave as. And also in terms of displacement, I can do the same thing, extract the displacement in the x direction from the second stage of my analysis. And like this, you can extract other type of data. For example, I want to see, I don't know here what to expect, but I want to see reaction force in the direction of total reaction force. Nope. Maybe we extracted something wrong. So stage 2, reaction force, let's say exactly. So I mean, this was not for this total reaction force. Yeah, bottom. And as always, what I can do is I can go through my result. For example, I have this in terms of displacement, I have this in terms of reaction, and I can unlink my database and create a new chart by copy pasting the results that I want to see. And I can see my hysteretic response. I'm sorry, guys, there's a bit of a lag. I mean, of course, in this case, maybe the selected accelerogram is not the best to show you this result, and it's a bit like foggy, but this is just for you to simplify, for you to see how you can create a specific chart, even if in the chart data, you can select 2 results as the base of your chart, but they have to be applied on the same selection. So if you want, for example, reaction force at the base and displacement at the top, you have to create different charts and then combine them as I just showed you. Unlinking the database, you are able to edit the chart. So there's not much more to say on nonlinear chemistry analysis in terms of basics. There would be a lot to say in terms of dynamics in general. I don't know if you guys have any question, if you ever tried to do nonlinear chemistry analysis, or if you want to add something for it, for me also to learn from you. And I don't know if you guys want to ask any questions also about any other things related to OpenSees and STKO. I'm available for quite some time, so if you need.
Hello to everyone.
Hi,
hello, Francesca. How can I do if I want to find the response of a particular node? So I want to create a personal record from the recorder. I want to create a personal record with the X displacement, for example, of a particular node. But the difficulty sometimes is where can I see the node? Because, well, under the mesh, it's easy to point and then we can see the node. But if we're in the geometry and I want to add the particular node and I want to see the label of this node, sometimes I have difficulty with this.
Okay. So there's many ways. Are you talking about recording the result in a monitor? So during the analysis and you do it in the preprocessor, or just extracting the result from the...
So I want to extract in a file the displacement, the time history of displacement of a particular node, not exactly in the monitor, but in a file. So I extend this in a file and I can open it later in another software. For example, I want to open it in MATLAB, so I will have a result of a text file. But what I have seen is that when I'm working and I have to go to the meshing part to select what node I want to record, but I think there will be a more easier way to do it.
Okay, so for example, using the monitor, it's like you can monitor, but you cannot monitor nodes of the mesh. Like, because in STKO you cannot, I mean, in this case, the mesh is like one, but if we divide our structure more, and we even within the mesh, we're not able to select a node that is not in the geometry.
Exactly.
The monitoring. So this node here, we cannot select it for a monitor. So what you're doing, if the node is not part of the geometry, you cannot do this. You can know the ID of the node. For example, I think here you should be able to know exactly, let's undo this, show node labels. So these are the nodes that are going to be written in your STKO files. So like here now you have the, let's say the ID of the node. And with this ID, you can even use the Python API to extract the value from that. I cannot explain to you that now because every time I need to develop a script, I need a little bit of time. But if you want, we can do that for you. Otherwise, there's another way for you to know this value here if you have a specific geometry that you want the nodes from. So if you create something called a region here, and then you, for example, select a specific, like all the master nodes. Okay, maybe this is easy, but if you select all the faces and instead of a region type, you give nodes and you write this on a text file, you will have all the IDs of this node. And this value here is like creating a variable in your, let's say, STKO environment. And with this variable in a custom command, you can actually extract the value with a normal recorder as you would do in an OpenSees script. So you go here, you go recorder, and you can just write the ID of the elements and etc. So like you would do in a normal STKO script, and it will be done not by the MCU recorder, but the OpenSees recorder. Otherwise, if you are in the postprocessor and you want to extract value from a single node, of course, you can use the chart. And once you have a chart here, you can copy paste this value in a text files. And if you create a chart that's linked to the database, every time you upload, you reload your database, the chart will be reloaded. Or you can also create, as I said, once you know the node ID, you can create a script querying the node. I'm sure there is. I'm going to show you where to look for this, because Dr. Petrarca did a few webinars on the Python API. So there is one in which there's a lot of material in it, and there's also a whole set of scripts to query information from either a node, a fiber, or a Gauss point. So here we have our first Python API example. So webinar number 20. If you download the files from this, maybe I already, yeah, no, I don't have them. I don't have them already. Just wait 1 sec that it goes down. But anyway, inside there you will find a lot of scripts in which there is one about query nodes. Yeah, it's not on the manual. I think it's just in the support material from that specific webinar. We still have to upload it in the manual of the Python API. So does that suffice your, like, do you normally already write scripts in which you extract the value from like a specific node with OpenSees? Hernan, I cannot hear you.
Sorry.
No problem.
Yes. I've been working also with the, yeah. Okay.
So for example, here, example postprocessor query node. Let's see what this says. I'm sure this is a bit complex. It goes into get database. The node finalizer identifier is host field. Okay, this is a whole script to create even a plot and to, I don't know if you talked about, if you heard about like using call types and the worker and the process thread and anyway, this is a bit more complicated to use. I would not suggest it now that I'm thinking about it. But if you want to write together a script on how to access a specific node and save the value in a specific text file from the Python API, but then I would suggest maybe that the fastest way is to use the STKO recorder inside of a custom command in your analysis steps.
Thank you very much, Francesca. It was very helpful.
Because in the end, if you think about it, that's the way OpenSees always record results. So you just want the classic OpenSees kind of output.
Thank you.
You're welcome. Sorry if I was a bit lengthy. So, Oguzhan, okay, so if I remember Massimo's webinar, did he apply the ground motion to the bottom face of the solid body or at a certain point? I don't remember that either, but we do have that file. So if you want, we can open it. So, but it's not a postprocessor, it's a preprocessor file. So if we go here, do you mean like in the implicit bridge? Thank you, Marin. So let's see where he applies. So you remember wrongly, Oguzhan, there's no ground motion here. There's just a uniform excitation. Ah, okay. This is one without soil body. There is one with soil body. You were right. Which one was it? Nonlinear time history about SSI nonlinear time history. So it's not the one about the bridges. Then I don't have the results downloaded. I think you understood up to now that SSI is not my forte. So you mean the only one that we have about nonlinear time history, right? Sorry, about cell structure interaction, in which there is a nonlinear time history analysis here. Probably, yes. What do you want to model with cell structure interaction, Oguzhan? What's your research about? While I open the file. Highway bridges considering SSI. Okay. So this was the soil structure interaction file. And we have an accelerogram of a wave. This was the base one. Then we do have, this one is not a nonlinear time history, I think. Yeah, transient analysis, horizontal load pattern. He created a load pattern in which it references just the constant one, and then another load pattern in which it references this wave with a specific factor, and inputs here a force called input soil. And this input soil is actually unitary force applied to the base of this solid structure. So, okay. So to answer your question from before, just to remind myself, you did not apply any ground motion, you applied a phase force and then used a load pattern to vary that force, which can also be done, but this cannot be done if you want to apply an input in terms of acceleration. And this was done from the bottom of the soil, yeah, bottom face of the soil. Okay, so you're studying highway bridges considering SSI and fragility curves. And in which like country are you based? Just like is your in Turkey? So your research is based on highway bridges in Turkey with like soil characteristic of Turkey, I guess, no? Just out of curiosity. Okay, that sounds very interesting. Even if I'm not very into soil structure interaction, as you understood. Anybody else has any more questions that you want to share or like information about what you're doing? There's been a few people joining in like very late. I've seen Julio couldn't like turn on his mic for a while. Somebody even joining just right now. Hello, hi, welcome. Unfortunately, our like half-an-hour session is just it's already completed, but I don't know if you have any questions or if you want me to show again the presentation. I still have some time to dedicate to you guys. Guzman, you want to know my email. So if you have any questions about OpenSees and STKO, you can just write on our forum. I'm just gonna post the link for our forum here. The forum is almost like my email, as I check the forum every morning. So just sign up for our forum. Hi, hello. And you can post your questions there. And if you have any also specific things, there's also private messaging you can use there to find me as, oh, sorry, I posted the link to Hannah. So this is the link. So first question, there's two questions, Faisal and Dr. Engineer. So Faisal, is nonlinear time analysis possible for measuring structure with micro and macro model? Of course it's possible. There was already a webinar on this. If you check here, I think micro. So cyclic, no, this is static analysis, not dynamic. But maybe there is something else. Cyclic. Yeah, anyway, it's possible because you can model masonry structures, you can model nonlinear time history, so this is something you can do. Micro modeling is quite complex and advanced, and you need to be, geometry needs to be, like it takes much of your time, and also parameter calibration, but with W16 3D, which is a plugin of STKO for OpenSees, you can model very good behavior of masonry, parabolic in compression and exponential softening in tension. So that's really a very good tool that has a very good convergence rate. Let's say it works quite well. So that can be done. So can we show cracks in concrete after nonlinear analysis? So cracks are not, crack width or crack extension, let's say, is not something that, that's not a result that you have as an output of OpenSees. It's something that you can create. So if you know how to compute a crack width, you can create something called a virtual result from the Python API. Of course, referencing the strain has the result that you're asking in your concrete model. I don't know which kind of model you want to see, probably a shell model of a shear wall, or a solid model of a beam or a column or a whole structure. I don't know what you want to model. If you want, you can also turn on your mic, and yeah, it can, I mean, cracks can be shown as the derived results of existing results like strain, and it can be computed through the Python API. Actually, we did something like this the other day in our team. So if you need that to be a specific tool that you want to implement, if you have a model that you want that to be implemented on, you can just post a question on our forum. We can send you the script that we use for that. But anyway, you can see damage that can actually show you as a, let's say, a default output that you can select in the recorder. And so if you have a model that supports material damages as a result, you can see also, let's say, the location of cracks. Maybe I can show you something in reference to this, if I find it. So let me just 1 minute search for the best. I think here I had it. Yep, so this one. Let me share my screen. Not this, but this one. So just for you to see what you can do with micromodeling, you can see the development of damage and also direction and extension of cracks in structures. Or if you're doing out of plane of masonry, or we even have a concrete solid example for you, where you can see the development of lesions in incremental static analysis. So cracks can be visible. If your geometry allows to see cracks and damage, if it's a micro model, that's much easier, or if it's a solid model. If it's just shells with a lot of number of elements, that also can help. So it depends on what you're modeling and what is it that you want to really see.
Hello, I have a question.
Hi, Gizan. Yes.
If I want to perform an analysis, I mean, I'm talking about the masonry wall, for example, but do I need the full license? Because I know that we could use a free version, but I think it's pretty limited, right?
Yeah, limited. I don't remember the number, but it's limited in terms of number of elements. So of course, if you want to do micro modeling, you need a lot of elements. And
even when my objective is to perform a macro modeling, but I saw some models that you posted, and they use a lot of nodes. So maybe I cannot do that.
Modeling, like equivalent frame modeling, for example, but that's not the only macro model that you can refer to. Even shells are macro modeling because you're just, I mean, the wall is, let's say, reference to has a large plate. So it depends what you do. If you want to do equivalent frame modeling of a small structure, maybe you need, I don't know, 15 edges and 60 nodes, maybe that goes inside of the free license. But if you do research, you can get like an academic license and through your university or your research institution. And that's a very good price commercially. It's not a commercial license. Commercial licenses are quite expensive, but academic license can be acquired through your university. Do you have a reference university that you work with?
Yeah, but I mean, I already have a model, but I did it in OpenSees. So what I catch my attention, it was a model that I saw in a course that it was a course about STKO in the south, in Peru. So I wanted to perform a model like that, but yeah, let me think about it, and maybe I could ask my supervisor if he could get the license.
Yes, I mean, you could just contact either info. I'm gonna just write to the email in the chat. Or STKO. I think these are the emails. I'm just gonna check to be sure. But
where did you send it?
What?
Where are the emails?
In the chat in Zoom. No, sorry, I sent them just to one user.
Yeah.
I'm sorry. Okay.
Okay, perfect. Thank you very much.
Yeah, you can just like put even your professor in touch with our purchase team, and they will give you all the information. But there's also a price table on our website.
Yeah, I think I already saw it. Yep, thank you.
I was trying to check out like what's the, let's say, what's the limit of the free license. I should also know what this kind of questions. Let me see if I found it. So you have a limit of 20 lines, 100 surface elements, and 150 solid elements. So 20 lines, probably you can do a small model of equivalent frame modeling of a structure with that.
Yeah.
And of course, if you create a user that has never used a STKO, you get a 1 month free trial. I don't know if you already used that, but that's also, it's unlimited. So you can, for 1 month.
Perfect. Thank you very much.
So Oguzan is asking me if I'm planning to continue the webinars with other topics. I don't know, we haven't planned it yet. We have some ideas. If you guys have any, apart from you that you want to do some structure interaction, I know that. But if you guys have any, we will ask you all for feedback and for also some input for next, let's say, educational programs that we can do. There's a lot of themes to explore, like surface elements, solid elements. I mean, we just started with frame structure, so we can go forward with other things too. We will see what we will decide internally. We haven't decided yet. But please, if you do have inputs or requests, you can always use our unused forum page that we created for this course. I'm glad you guys are anyway following good, but there's a get started discussion, and here you can just post a new thread saying, I want to know about this, and please do make a topic about it. And if we account for more people that want to know specific topic, we'll be able to. Also, if you want to involve universities into teaching and learning STKO, we will be willing to collaborate. So just let us know. Hello, Dr. Engineer. I think you did another. So can I consider the nonlinearity of RC slabs during nonlinear analysis of building? Of course you can. Did you follow any of my previous webinars, or this is just your first time? Just to understand what I should repeat or not. Hello? Maybe your mic does not work.
Hello.
Hi. Hi.
Hi.
What's your name?
Dr. Ibrahim.
Hi, nice to meet you. So did you follow any of the previous webinars, or this is just your first time? Okay, anyway, regardless. So we just talked about 3D frame structures and not about how to model, for example, shells for slabs. But there is the possibility to use, for example, something called a layer shell, which is a fiber layer section of a plane element. And into that, you can include a nonlinear material that kind of accounts for the biaxial behavior. And you can include nonlinear analysis, like nonlinearity of the slab. This can be done. If you want to model specific slab, let's say in their specific geometries, like if you have RC with reinforcement and you want to model the reinforcement has beams, and then go through model the concrete section as a shell, that also can be done. So there's a lot of different things that can be explored. We don't have examples of like nonlinear slabs, but if you guys are interested in something like that, we can put it as a topic for our next series. Anyway, so I'm going to write down maybe write a script for a none on how to query a specific node and save the result in a external file that can be useful for other people too, and we can put it on our manual. And I think for today we are done. Thank you for participating. Thanks a lot, and I'll see you guys next week. We have week 17, and then we have only 3 weeks after that. So call your friends. So the more the better. And enjoy the rest of the week. And thanks a lot for participating. Thank you all. See you soon. Bye.